This conference will now be recorded.
All right, this is Math 211, section 3.4. We are still just a tiny bit off of where I wanted to end today. So I want to go through and do a few more of these limits at infinity and talk about the horizontal asymptotes again. So just to kind of recap what we were doing in class, we learned that um, when we talk about something being a limit as x approaches infinity or negative infinity, we're saying as the x's get extremely large in either direction, so very, very, very far out there, the end behavior, are we approaching a value or are we going off to either positive infinity or negative infinity? Or there'll even be a case sometimes where there is nothing that's really happening, and I'll show you in a minute by what I mean by that. So when we talk about these, remember we're looking at them from the right or the left, depending on if we're doing positive infinity or negative infinity. So here are just the picture reminders of kind of what we were talking about in class today. And we said that if the limit actually exists, so we get an L value, a number, that would then be y equals L, and it is the horizontal asymptote. And then we had this picture where this someone had two different horizontal asymptotes, one for the right side, one for the left. We also talked about this theorem that said if r was greater than 0 and is a rational number, so that means either an integer or a fraction, then 1 over x to any power that has got a positive rational number is, remember we said no matter what, if you keep making the bottom bigger, 1 divided by that is going to get smaller and smaller. And as you go towards infinity, it gets so close to 0 that we can say it approaches 0. Same thing for the negative infinity. This would still hold true. This is the graph that kind of shows that picture, that's approaching 0 on both sides. And we said that that was really important to help us evaluate limits at infinity for rational functions. We would find the biggest power in the denominator and divide everything in both the numerator and denominator by that highest power. And then we look at how those individual pieces reduce and apply our limit laws. There is sometimes the issue where you'll have a radical in your function that might have a plus or minus between it and another term, and you might need to use a conjugate. I will save that one for in class together to make sure I show you that specific example. And then we didn't define this, but I wanted to define it now, and I'll again briefly mention it again on our next class session. But infinite limits at infinity. So the notation, the limit as x approaches infinity of f of x equals infinity, is used to indicate that the values of f of x as we go towards the farthest we can to the right and left become those y values become very large as the x values become very large. And that could be applied in many different ways. It could either head to positive infinity on the graph, which means headed up forever. As you go to the right, you could be headed down forever, so towards negative infinity. As you approach the farthest negative number you could be headed to positive infinity or negative infinity. What that tells us then is that there is not a horizontal asymptote on that side. So we would not have a horizontal asymptote at that specific value because remember, an idea. Infinity is not really a number. So just some notation about illegal cancellation. I see, or just illegal writing stuff, legal notation in general. You cannot write the following as how you would evaluate this, because notice this doesn't have any denominator. So we can't use the divide by the highest power in the denominator to create those 1 over x's that make go to 0. So we can't use that property here. And if you plug in anything into that's an arbitrarily large number into either one of those, they're going to, as they get bigger, these numbers are going to keep getting bigger. And we can't just break it apart and say that's infinity minus infinity. That doesn't make sense since infinity is not a number. So the better way to deal with something like this, where you don't really have a way to divide out any terms because there's no denominator, is to factor it and talk about it this way. So x times x minus 1 is a product. And x and x minus 1 are both going to get extremely large the farther out x goes. So if you have two very, very large numbers and you multiply them together, it's going to be very large as well. And remember, arbitrarily just means, how large are we saying? So that product would go to positive infinity, okay? Now, this is just the precise definition of a limit instead of what we used in our own words. It says, at infinity, says let f be a function defined on some interval a to infinity, then limit as x approaches infinity of f of x is L, means that for every epsilon greater than 0, there is a corresponding number n such that if x is bigger than n, so that's our point on the x-axis where we say we've gone far enough, and after this point, the graph stays in a neighborhood around the limit. So here's a picture of this. Once you get to that certain very large n, if your x's are bigger than this, after that point, everything in the graph is within your epsilon neighborhood of your limit. So it's either in L plus epsilon or L minus epsilon. And remember, we could set epsilon as small as we want as long as it gives us a neighborhood on both sides of L, but we would probably need a larger and larger n the tighter we make that neighborhood. So same thing can be done for the other side. I just put one picture here so you could see that. And then the definition of an infinite limit at infinity means that this is the official definition. Let f be a function defined on some interval a to infinity, then the limit as x approaches infinity of f of x equals infinity means that for every positive number m, so that's this y value, there is a corresponding positive number n such that if x gets bigger than n, then f of x has to be getting bigger as well. So what they're saying is no matter what x we pick, if you pick a bigger x than the number you just were at, your y value should also be getting bigger. So it's increasing without bound. And you could do the same thing for the negative case. It would be getting smaller in each direction. So I wanted to do just a few more of these, just so I left a couple for in class so we could do them together. But let's look at this one. It says we're evaluating this limit. That was our directions. Find the limit or show that it does not exist. And this one's a little bit different because it has a square root in it. So this would be the limit as t approaches infinity. And we're using the highest power in the denominator, which is t squared. So remember, you could write t to the square root as t to the 1/2. So we have that divided by t squared plus t squared divided by t squared. In the bottom, we have 2t divided by t squared minus t squared divided by t squared. Okay, so let's work this out. So this would be limit as t approaches infinity. This is 1/2 minus 2, so that's going to be a negative 3/2, so that's still going to be in the denominator. So 1/3/2. This would be a plus 1. This would be a 2 over t, and this would be a minus 1. Now what we learned in that theorem a minute ago was that as t goes to positive or negative infinity, either one, a 1 over or a number over a t to a positive rational power of any rational kind, which means integer or fraction, will go to 0. So that means this is 0 plus 1 over 0 minus 1, which is just 1 over negative 1, which is negative 1. So that would be the limit of that, which means if this guy on the right side towards positive infinity is approaching a horizontal asymptote of negative 1. Okay, let's look at another one. So I'm saving D and E to do in class since they're just a little bit different, especially since that one has a radical that has 2 things inside. So I want to talk about that individually. This one also has a radical with 2 things inside. So let's talk about this guy right here. Now, because there's no denominator here, we can't use the trick to divide everything by the highest power of the denominator. The only thing we could do is we could factor out that x squared. So that would be x squared times 1 minus x squared. And then we could do the limit as x approaches infinity of x squared times 1 plus x and 1 minus x, because that does factor again. And we could talk about individually each factors, right? So as x squared gets plugged in bigger and bigger x's, it's squared. It's always going to end up positive. It's going to keep getting bigger and bigger, and it's going to be positive. If you do 1 plus really large numbers, guess what? You're still going to be positive, and you're going to be really large. And if you do 1 minus really large numbers, that's going to end up with a negative sign overall. So because of that last factor, this whole thing is not going to positive infinity. It will end up going to negative infinity. And this is one of those that the graph just goes down forever as it gets closer and closer to bigger and bigger x's. So just realize that they don't always go to positive infinity. Sometimes as you go to the infinities, your graph is going down forever instead of up forever. But remember, this means that at that direction, we would not have a horizontal asymptote, that is approaching. Okay, so what other ones did I want to do? Let's look at this guy right here. So this is limit as x approaches negative infinity. This one does have the fractions, so we can divide by the highest power in the denominator. We can use that trick to try to use that theorem. So this would be 1 divided by x to the fourth plus x to the sixth divided by x to the fourth over x to the fourth divided by x to the fourth plus 1 divided by x to the fourth. Now, this would be then the limit as x approaches negative infinity of 1 over x to the fourth plus x squared over 1 plus 1 over x to the fourth. Now we know both of these guys, as we plug in that going to negative infinity, they're going to 0. So the problem is we still have an x squared on top, and we have this 1 in the bottom. So if you keep plugging in negative numbers that are bigger and bigger, and then you square them, it actually is going to approach positive infinity because you're squaring it. That means that the sign is going to turn positive, and the bottom sign is also positive. So this is headed towards positive infinity. All right, let's talk about h for a second, because h is a special one. Because remember, what does sine of x look like? Sine of x looks like this. It starts at 0, 0, and it goes up to 1 at pi over 2, back to 0 at pi. At 3 pi over 2, it's at -1, and at 2 pi, it's back at 0. And remember, the sine graph continues that pattern forever and ever. And I'm not going to draw very neatly here because I'm way off the grid, but it continues that forever. So this one, no matter what you do, it's never getting closer and closer to a specific number. It stays fluctuating, or what we use the word is oscillating, between -1 and 1. It's never going to change the distance. The distance between those two oscillations never get closer together. So this one actually does not exist because it forever oscillates between -1 to 1. Okay, so it's not going to ever find a place where it's converging down to a singular value. All right, let's talk about I. Again, the highest power in the denominator here is x to the third. So we will take everything and divide it by x to the third. So this would be x to the fourth divided by x to the third minus 3x squared divided by x to the third plus x divided by x to the third over x to the third divided by x to the third minus x divided by x to the third plus 2 divided by x to the third, which means we have the limit as x approaches infinity of x minus 3 over x plus 1 over x squared over 1 minus 1 over x squared and plus 2 over x cubed. Remember, all of these individual rational fractions, as x's get larger and larger, those are going to go to 0. So the problem is we have this x that's not being divided out over 1. 1 is positive, so what's really going to matter is what's happening on top. If your x's keep getting bigger forever, this value also keeps getting bigger forever, and it's going to be positive. So this is going to positive infinity. Okay. Which again, if we're asking about the horizontal asymptote in that direction, we don't have one. Okay. All right, and for this next one right here, this is a square root of x squared plus 1. Again, no denominator, nothing to divide by, to use our little trick here for the zeros. So when we're looking at this, we're just asking ourselves the question, what's happening as this is going to infinity? Okay, because it's going to positive infinity. So we're squaring this number and then adding 1. So as x goes to infinity, x squared plus 1 also heads to positive infinity, okay, because it's still going to just keep getting bigger and bigger. And we're taking the square root of that. Now, if you take a square root of 3 and then a square root of 4 is bigger. So the square roots will also continue to keep getting bigger and bigger. It doesn't look like they're growing as fast because you're taking a square root, but they are continually forever getting larger. So this one also goes to positive infinity. All right, and that's going to be the end of this video because I want to leave the asymptotes and the formula part for class discussion. So all we have left is just a couple of the ones I skipped over, just to make sure we get a little variety in class. And then we have to, how do we find the asymptotes of all different types? And how do we write the formula that satisfies a condition? So we will pick that up on Thursday's class, and we will also do our curve sketching notes that day.